Hi, my name is Mark Thorne. I'm the Application Engineering Manager for Mixed Signal Products at Linear Technology, and today I'm going to tell you how to use one of our Easy Drive Delta Sigma A to D converters to make thermocouple measurements. Temperature is arguably one of the most measured physical phenomenon, and there's a lot of sensors to choose from. Thermistors are highly sensitive, and platinum RTDs are very stable and accurate over time. But thermocouples, in spite of the fact that their accuracy is quite low, a few degrees centigrade, and the output voltage is quite small, microvolts per degree C, they still find wide application because they're very rugged and very cheap. So here's a schematic of how a Type K thermocouple would typically be applied. The way a thermocouple works is it's two dissimilar metals in which a temperature gradient along the wires produces a voltage gradient. And the two different materials have different gradients that result in a net voltage difference at the cold end of the thermocouple. So a Type K thermocouple has an output of approximately 40 microvolts per degree C. And that's the difference between the hot end of the thermocouple and the cold end. So the classic way of dealing with the cold junction is to actually submerge the cold junction in an ice bath to hold it at 0 degrees C, so there's no offset term. From there, the output of the thermocouple can be amplified up to a reasonable level and either digitized or displayed on a meter. Another way of dealing with the cold junction is to use one of our old devices, the LT1025 cold junction compensator. What this device does is it drives the negative terminal of the thermocouple to the same voltage that an ice bath would have driven it to, and the positive terminal can be amplified in the same way. The LTC2492 is an Easy Drive Delta Sigma A to D converter, and it can replace the amplifier and the cold junction compensator, and it's basically an all-in-one thermocouple digitizer. So a couple key points are that the cold junction of the thermocouple needs to be in thermal proximity to the device. The 2492 has an onboard temperature sensor that gives about a 90 microvolt per degree C signal. So this can be used to calculate the cold junction voltage in software. Another important concept with the LTC2492 is that the sampling currents from the positive and negative input terminal are equal. So in this configuration, there's about 800 nanoamps of sampling current flowing through the thermocouple and into ground through this network. So adding an RC network provides a couple of functions. It does provide a little bit of noise filtering coming into the A to D converter, but it also averages the sampling current over the course of a conversion. So it makes the inputs very benign to drive. You can get rid of a lot of that sampling current by biasing the thermocouple negative terminal up to about half of the voltage reference. So this would be useful in an application where the thermocouple is floating. Grounding the thermocouple is a great way to reduce noise and make the whole system more rugged. The voltage reference is provided by an LT1790 1.25 volt reference, and the interface to the microcontroller is through a standard SPI interface. And now let's have a demonstration. So here we have a complete handheld temperature thermocouple meter using an LTC2492. Here's an LTC2492 reference board that has a thermocouple socket attached to it, an LCD display displaying lots of useful information, and a little microcontroller board for control. We've also got a commercial thermocouple meter to compare it to. We've also got a specially modified toaster oven with a PID controller that gives about 0.1 degrees centigrade stability to make it a little more useful for calibration purposes, and a quartz resonant thermometer to compare both of these against. And inside the oven we've got the quartz probe and two thermocouples all in close proximity. So let's look at a few of the numbers here. So the calculated thermocouple temperature is about 79.9 or 80.1 degrees. We've got a couple tenths of a degree of flicker, which is about what you would expect given the 600 nanovolt noise of the A to D converter itself, which compares quite well to the 79.8 degrees read on the commercial meter. And we're still a couple degrees off from the quartz thermometer. It's different sensors, and this is not exactly a first-class calibration setup. Some other information, and this will help with understanding how these meters work a little bit better. We've also got the thermocouple voltage, which at 80 degrees centigrade is about 2.3 millivolts. The cold junction temperature is about 23.8 degrees centigrade, which is the temperature of the internal temperature sensor. The PTAT voltage, or the voltage output from the temperature sensor inside the A to D converter, is about 27 millivolts. And the calculated cold junction voltage is about 0.95 millivolts. And as we saw before, the cold junction voltage at room temperature is about a millivolt. So this voltage is subtracted from the thermocouple voltage, and temperature is calculated from that. It's also a good idea to test unexpected situations. So here we've got the case where the thermocouple meter, or the so-called cold junction, is in an oven at 75 degrees centigrade, and the thermocouple is in a block of dry ice. So that's a way to test out how good your cold junction compensation is. So here you can see the thermocouple temperature is at about minus 89 degrees centigrade, and this meter is reading about minus 93 or so, so we have a little bit of discrepancy. The thermocouple voltage is at about minus 6 millivolts, which illustrates another nice point about the LTC2492. It's perfectly happy digitizing signals a little bit below ground. The cold junction temperature is about 73.2 degrees Celsius. The temperature sensor voltage is about 32 millivolts, and the calculated cold junction voltage is about 3 millivolts, compared to about 1 millivolt at room temperature. If you were making a thermocouple meter, you'd want to use a proper thermocouple simulator, but you have to admit that this was a lot more fun. So if you have a thermocouple application, please visit our website, or also please feel free to give me a call.
Left him!